Hi, Facebook people. Hopefully you're out there watching. Welcome to AEON3. So for everybody here, how many people here, just by show of hands, have not been to an AEON3 meeting before? So a number of you. Okay, good. So let me start with an explanation of what AEON3 is. And do I do that first? Sometimes I get confused on what I'm supposed to do. Oops. See, I'm already screwing up. That's how fast that happens. So an overview of AEON3. So for hundreds of thousands of years, mankind lived at the whim of nature. We moved around the planet, we scrambled for food, we kept ourselves alive, and we were consumed with the simple matter of survival. That was the first eon, and that lasted for a very, very, very long time. The second eon started occurring, it's debatable on the exact date, but somewhere around 3,500 and 4,000 years ago. We suddenly started writing things down. And what that occurred from is an ability for Homo sapiens to recognize shapes. If you know what a triangle is, you know what an arrowhead is. This leads directly to art, writing, symbols, runes, the modern world, computers. All of that is the ability to recognize shapes, which suddenly emerged in Homo sapiens all over the planet simultaneously at one time. It's a very strange phenomenon. There's a really good book called Guns, Germs, and Steel that I recommend people read because it's a great read, and he really nails that moment. A lot of study has been done to try to figure out what happened, and there's a lot of theories, but right now it's still kind of a lot of theories. So that was the beginning of the second eon. We're still in the second eon. We write things down. We're in the information age, right? We call it that today. But that's just a massive amplification of writing things down. The third eon is when we escape nature and we're no longer really under nature's thumb. We become something different than we are today. Not organic, not natural, not part of nature, kind of away from nature in a different way. That's the third eon. And I've spent a lot of time trying to explain that over various meetings for a very long time. Watch them on YouTube, they're a lot of fun. Their YouTube channel is just called, if you just put in AEON3, it'll show up anywhere you want. So that's an overview. Any questions from the overview? Okay, good. I feel I'm doing my job then, okay. So our sponsors, thank you for the dock, for giving us this space. I own the dock, so it kind of works out good because I give this space to myself. So I really am appreciative of myself. So, and also from Blue Flame Coffee. Hey there, how are you guys? And Blue Flame provides the coffee. There's free samples of Blue Flame coffee. They're an importer roaster in the back, and they're just awesome. They do a great job for us. Everyone here at the dock community just loves the Blue Flame coffee and gets down it as much as they can, so it's good stuff. Okay, tonight is quantum computing. So just by a show of hands, how many people think they understand quantum computing? 2, 3, 2, 2.5. I'm gonna go 2.5, 2, going 2. Okay. Okay, so why are we building quantum computers? That's the first question that you should be asking. Why are we doing this? Why are we going down this path? What's wrong with computers of today? They work great, right? They're moving along. Anybody remember this guy? Gordon Moore, CEO of Intel, came up with a really cool idea that processing power, the number of transistors we can squeeze onto a chip, would grow exponentially. He came up with Moore's Law. So there it is, from 1960 into 2014, the number of transistors per CPU would grow by a nice, even scale. It would just work that way. Now, some of this has been perpetuated by Intel, releasing chips at exactly the right time to follow Moore's Law. But sometimes there's a lack of innovation, and sometimes there's an overabundance of innovation. And I think if you allow for that, you actually get something that looks very like this. I think it's a very good rule. It does really work like this. But there's a problem with silicon transistors on a CPU. The problem is really simple, and it's kind of silly. It comes down to physics. When you're putting more and more transistors onto a single CPU, you run out of etching space. The technology we use to etch the chips only allows for so many nanometers of separation of wires, basically, on the chips, on the circuits. We've been using different techniques for the last 10, 15 years to make those wires thinner and thinner and tighter and more packed, making the CPU chips now. We can't make them on the size chip we used to, right? Who's seen a brand new CPU today? especially one for a large enterprise computer, multi-core CPU. They're getting bigger, aren't they? It's like we're going back in time. They're getting bigger and bigger and bigger. The reason they're getting bigger is this. The end of Moore's law is upon us. So Gordon Moore himself originally said this would end in 2005. It just wouldn't work after 2005. He didn't know why. He said that a long time ago. There's VSLI said, Dan Hutchinson said 2003. Isaac Chuang from IBM Research said 2020. Now you'll notice when you switch from the blue to the orange are people saying it's the end due to a technical limit. We just can't squeeze more transistors on a chip. As the chips get bigger and bigger, the distance between the transistors gets bigger. No matter how small you make the wires, you're running into a physical end of silicon-based transistors. The end of Moore's law. The end of this type of computing. All you can do is build more processors and then divide programs up better. But you're not going to get true exponential growth in processing power like you did in the past. And there's lots of other, what's interesting here is that Gordon Moore later said, okay, it'll end by 2015 to 2025. And then he revised himself again saying, it's going to be 2025. But no matter how you slice that, there's only one person, two people actually, Lawrence and Glenn, they're from CERN, that say approximately 2600, but that's using a different kind of technology. For most people, we're looking at between 2015 and 2020, which is now, the end of Moore's law, which means we're at a standstill in computer processing power. And you guys all feel this, don't you? Your computers aren't growing the way they used to. They're kind of stagnating. And now we're adding more and more layers, and I can't buy a more powerful processor. I buy 10 processors and I stack them. And each one is still that 2.63 gigahertz thing. What's wrong with that? Why can't I get it faster? Because that's why. You're at the end. So that's why we need to have a new, brand new, totally different kind of computing that's not related to this. Everybody with me? Because that was a pretty complicated thought. Sir, use the mic. Oh, you are with me. That was a thumbs up. Okay, sorry. Never mind. Okay. So this is the question everybody wants to know. How do quantum computers work? So we're going to enter into the realm of the weird. And as we go through this, it's going to get weirder and weirder and weirder, and then there'll be lasers. So just hold on, okay? So basically how they work, there's a quantum computer. Look, it looks just like a regular computer, right? It's that thing right there. It's just on the end of some arm, and there's all those wires coming off. That looks like a hobby kit I built back in like 1985. There it is. A quantum computer uses a phenomenon to perform operations on data through devices using things like superposition and entanglement. A traditional computer uses logic gates, mechanical circuits, transistors, which can be calculated by classical mechanics. So one is a mechanical machine. I can't get that into your brains enough. A traditional computer is a mechanical machine. A quantum computer is using the universe itself, the rules that govern the universe, as a way to do calculations. And we'll come back to that again and again and again tonight. So, oops, hey, don't do that. Why does it do that? Too fast. Nope. There we go. Nope. There we go. Okay, so a classical computer has zeros and ones, right? It's either on or off. It's binary. Everybody with me? Everybody good? Everybody understand that? Okay. A qubit, which is a quantum computer, uses something really different. I'm going to have to kind of point to this to help you guys understand. And if I'll kind of go this way, I guess. No, this way, I guess. And then I'll do it again. So, ooh, wow, that's loud if you're right by that. So this is 0, and this is 1. And this is 0 and 1 at the same time. It's the potential of being 0 or 1. So when you think about that, I don't just have 1 and 0. I have 1 and 0 and the potential of being 1 and 0 all at the same time. So right there is an order of magnitude in computing. That's not the whole thing. Did you guys get that in your way? Is it all, everybody okay? So 0 and 1 and 0 or 1. Okay. We're going to come back to that again and again, trying to understand that, because it is really confusing. And at some point, you're just going to throw your arms up in the air and go, I'm lost. And then start yelling at me through the microphone and everything will work out. So how much better are quantum computers? Why is this cool? What do they give us? Why do we need to make this big leap? So they use the power of atoms and molecules. It's the very structure of the universe to perform processing tasks. And here's one of the greatest things. A silicon-based computer does everything linearly. One process at a time, followed by another process, followed by another process, followed by another process. These things, and the way we achieve parallelism or parallel processing is multiple processors, right? We stack processors. But it's still linear. It's kind of a lie, right? This does true parallel processing. It can be thinking about and working on millions of things at the same time. So not only is it more orders of magnitude in terms of the registers, the on-offs, it also can be doing things simultaneously, which is really confusing, but again, I'll come back to this again and again. There's a really easy answer. A 30-qubit quantum computer equals the processing power of a conventional computer running at 10 teraflops, which is trillions of floating point operations per second. That helps, right? No, it doesn't. This is a better one. So to search the Library of Congress to find someone's given name, McCandless, in the whole Library of Congress would take a traditional computer today about 100 years. A quantum computer could do it in 1/2 of a second. Because it's doing parallel, right? It's not linear. It's thinking about many things simultaneously. Did you have a question? No. Okay. That's corner of my eye, sorry. Okay, so what is superposition and entanglement? That's for the, did I nail the things that earlier on you were like, I don't get those things, of the things I mentioned? Teraflops, you know, it's just lots of flops, but these two are a little more complicated. Okay, so we got to talk about Schrodinger's cat. Who knows about this cat? Raise your hand. A few of you. Okay. So we don't have a cat, but we do have, I'm all right, ain't nobody worried about me. This is the chipmunk from, it's a gopher. It's a gopher. Cinderella story. What's the name of the movie? Come on. Caddyshack. There you guys go. This is not the chipmunk. No, gopher, whatever. If I do this, though, he looks really funny. Okay, so this is a box. I'm going to take Schrodinger's cat, or the gopher from Caddyshack. Did he have a name? Mr. Gopher. We're going to put Mr. Gopher in the box. Then we're going to take this device. Now this device has an explosive poison bomb in it that will go off randomly or not go off. It's got some type of a machine in it that will randomly choose if it releases the poison in here and kills Mr. Gopher. Sorry, Mr. Gopher. And then we close the box, so we can't see inside of it. Right now, is the gopher alive or dead? Right now, is the gopher alive or dead? That's superposition. Both positions are true, and both positions are false simultaneously. The truth is revealed, and all of the alternatives fall when I open the box. That's quantum mechanics. Get it? Everything happening simultaneously, but until I observe it, I don't know the answer. That bit, the qubit, the potential of 1 and 0 is there, but I don't know the answer until I observe it. Another example, one that I watched online today, a really good video on YouTube. There's a British guy, super funny. He's standing in a queue, because that's what British people do, right? At the grocery store. And then as you go through this one line, there are 12 registers. That's a superposition of 12. You're going to go to one of them, but there's no way to know which one. And you started the path to the one that you're going to wind up on when you got up and brushed your teeth in the morning. The entire path to the register that you're going to wind up at is all part of the superposition until you go to one and all the other potentials fall. Got it? Another way of saying it. So he used an example, and I'm quoting a guy from YouTube who's really good. And he said, I'm trying to think of there's a guy walking towards me, and I don't know his name. I know him, but I don't know his name. He's one of the Beatles. So it's either John, Paul, George, or the other guy. But I don't know which one because I'm not a big Beatles fan. But I want to say hi to him, right? So your brain, this is how human brains work, right? We start doing the probability matrix. It's probably this, probably that, probably this, and you come up with different numbers, right? And those numbers are shifting constantly. And each time you observe them, you can get different results of the superposition until you choose one. So it's not just two, it can be many, many, many superpositions, an unlimited number of superpositions. I know it's confusing. Do you understand the concept of yes, that, superposition. Do you guys get the concept of it? Until you look at it and choose one and it's revealed, it's all available. I just want to check. It's not pretty. It's not pretty. Okay, that's Schrodinger's cat. You guys are doing good so far. Okay, any questions so far? Nope, okay. How about entanglement? That was weird, so how about entanglement? For entanglement, we're gonna need to do something different. Ooh, let's do this. Wait, this is complicated, so I gotta push buttons. That's the volume button. That's not the right button. It has the potential of being any of these. It's a superposition. Darn it. Oh, that says it's AV2. Okay, I'm gonna walk away. Don't do it. Okay, here we go. So, Bob making a wave. Take one. Here we go. So if I do one wave at a time, see the wave? It's nice and even and beautiful, isn't it? I could do it that way, or I could do it this way. It's a beautiful, even wave. Even waves across the tank. But if I take two of them and I do it simultaneously, look in the middle. See how the waves are canceling each other out? If I start to do them in opposition, they don't cancel each other out. But if I do them again, watch the far side of the tank. Watch the far side of the tank become still. You guys get it? So the reason that's happening is as the wave propagates across the tank, they start to hit each other and they interfere. That's called an interference pattern, which is the first thing to understanding entanglement. Got it? Everybody okay with that? Tank is pretty simple. It's a tank of water. You've all done this in the bathtub. Admit it. Now I have to switch back. Here we go. Going around the horn. Go. Okay. I feel good about that. Do we have more to see? Oh, hey. Okay, while you guys read this, I'm going to have to switch you to something else that will help you understand. I need someone's help lifting the quantum laser cannon. Andrew, would you assist me with the quantum laser cannon? It's in here. And you'll need to shift a little bit one way or the other. You will need to shift one way or the other because we're going to set it right there and it's going to shoot at that white target. But don't be alarmed. It's just a laser cannon. So the most important part is don't touch this area. Okay. Because it's very delicate. Yeah, and that is the area. Oops, that's the area that goes towards the board. So we're going to come in right where that guy's standing in the leather jacket by the wine. Okay. So go right or left. That's good. I like it. I like it. You guys like this? We're going to go right there. Don't be scared. Okay. This goes right about here. Then we aim the laser cannon. Okay. That doesn't look right, but I'm going to go with it. Okay. Here it goes. Well, it was. I'm worried that I'm not seeing a target. It's terrifying when the laser cannon moves. Yeah, that's okay. That'll work out. Don't worry about that. Ooh, mood lighting. I'm all right. Nobody worried about me. My tape is lame. This is the lame part of the show. Because you know when I pull this on, it's going to totally wreck it. Oh, it didn't. Cool. Okay, go there. Okay. Now, what do you guys see? Hans says we see nothing because it's dark. An interference pattern. This man wins the Cupidol right here, right here. So remember when the waves in the water tank hit each other and cancel each other out? That's the same thing that's going on here. This is the bright one in the middle, right? So there's two little bars over there, two little slits, like this. And as the photons go through the two little slits, there's a slight angle that they have to go through, right? Individual photons. And as they go through the angle, They make bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. Get it? So what's happening is, let me try to explain this. So as they're going through the two slits, remember light is a wave, right? And a particle. So as it's going through slit 1, the deviation of the two, they get out of phase. So instead of being like this together, because it's one phase off, they get like this and they cancel each other out. That's the dark bits. Then as you move farther, because it's one more phase, they move from being out of phase back into phase, and you see the light. In the middle, of course, they're all right together on the same wavelength. So it's as they move out through the two slits, you get this interference pattern. Everybody with me so far? It's pretty simple. Except that's not the part that's cool. Would I get this? So the idea being is that the particles of light, as they go through the slots, are interfering with each other, canceling each other out. That's what causes the dark bands. And then realigning. What if I sent the photons through one at a time? There'd be no chance for them to collide or cancel each other out. Everybody with me? So if I do this, and I had a little photon generator over there, and I could have it kick out photons one at a time, which would take a room a lot darker than this one for me to record it, I get the exact same pattern. Now I want you guys to think about how that's possible while I go turn the lights back on. The reason that they're doing this is because the particles are intertangled. Intertanglement is one of the hardest things in the world to understand, other than how to track me with a camera. That's also a really hard thing to understand. So we should probably take the tape off that and turn that off before I blind myself. Can you just reach around to undo the tape where you saw me tape it on there? To turn the light off. There you go. Perfect. Thank you. So now I won't have to go blind. Did you guys read this? Okay, good. Just making sure. Okay, so the particles are intertangled. That's why this pattern occurs even though you're shooting the photons through one at a time. So the patterns that we see in waves where they interfere, we think it's the particles colliding. We thought that for years until we figured out this experiment where you send the particle through one at a time, which means if you sent through one atom of water at a time, which would be really hard, but if you did, you'd still get the same wave interference pattern. How is that possible? Because the particles are intertangled. They don't think that they're two different particles. They think they're one particle. This is hard to grasp. Every particle in the universe doesn't think it's an individual. It thinks it's all one particle, because they all came from one particle, and they are all still part of one particle. The Big Bang, to our perception, created the universe. To the particles in the universe, they're all still one particle, still connected, still one thing. Understand? You don't have to understand, but at least get what I'm saying. I told you it was going to get weirder and weirder. It's going to get weirder as this goes on. Okay, so what can we use quantum computers for? Lots of stuff. Man, simulations, physics, chemistries, material science, nanotechnology, biology, medicine. It can compute millions of variables all at once. We don't have to wait linearly. The problem today is we can't simulate these things. It's one of the reasons we have trouble building new disease-killing treatments and things, and building new computers and dreaming up new cryptography, and all these problems is we have to wait for that damn computer to do things one at a time, right? It takes forever. It takes forever. You start doing things with big numbers, which is, of course, what we're doing now, right? We're crossing into big data. We finally figured out when we start looking at all the data, and we're not even looking at little things. We're still looking at big things that don't produce much data. You start trying to look at the superposition of a particle in the known universe, all of them. That's a lot of data, right? You can't do that with a traditional computer. You have to have one of these. Cryptography, this is the end of hacking. You'll never be able to break quantum cryptography. It's just not possible.
Is there an actual quantum computer?
There are many quantum computers. So the question was, are there any quantum computers? There is, and the order of magnitude they're growing right now is crazy. Google, a few months ago, said, we got this, we're going to create the world's first 30 qubit computer. IBM just announced a 42 qubit computer. They just took and that's not even the interesting thing. The interesting thing is, so far up to this point, the quantum computers have been built using specific software to do specific tasks. They're actually engineered to do a single task, calculate a floating point variable, just that task. Now, they're starting to be more ubiquitous. The way that we're actually designing them is changing. And I'll cover a little bit of that later. I'll show you some bookmarks from YouTube just from today that were amazing. Concepts that said we'll never do this, or they can't do this, or we can't go here, or this isn't possible, are falling by the wayside faster than we can say falling by the wayside. And the reason is because this is brand new, right? The cornerstone of AEON3, of the third eon of mankind, is quantum computing. It's what makes artificial intelligence intelligent, not artificial, right? Because it has that kind of power where the things that we're dreaming up in our minds, it can make possible. Understand? Because of this. And safe, right? Oop, that was supposed to be the punchline. So, what does all this have to do with AEON3? And what it has to do with is this thing, time. Here's the problem. Everything I showed you, and the reason you don't get this is because you're thinking the way you've been taught to think by everyone you've ever met in a position of teaching. And it's fundamentally wrong. All of the math we use is wrong. Everything we touch is wrong. Because everything is rooted in time. You guys know that this messed up Einstein, right? When he got to the end of his career, he realized that everything he was doing was wrong. He had been focused on light and waves and particles. And when he got to the end of studying them, he realized, shoot, I should have been studying time the whole time. Here's the secret. The reason that when you shoot the things through one photon at a time towards the target, they create the interference pattern, is because there is no such thing as time. It's never existed. It will never exist. You even know it doesn't exist because you know from relativity and superrelativity that a moving object affects time, right? If you go up to the highest peak on a mountain on Earth, time moves at a different speed than it does sitting on the surface of the planet. Because time is an illusion of where we're standing in the universe. Quantum mechanics, quantum computers don't know what you're doing. They don't know what you're thinking about. They don't know what you're talking about. They do everything simultaneously because they don't understand the concept of time because it's not real. Now your noodle's a little baked, I can tell. So to help you, because I knew this you'd be stumped right here, I got handouts. You can just take one and pass it around. This is a difficult concept. It's difficult for everybody. But almost all physicists now have moved to this position that they all pretty much understand that this is the true nature of the universe. The universe doesn't understand there was a Big Bang. The universe still thinks we're one particle. We're one thing all together at the same time. When you think about storing data, using quantum inference, the stuff with the little things here, quantum entanglement, this table is made up of some type of wood-like product, right? What's it actually made up of? Think smaller. Atoms. Is that you? Good job. Atoms, right? Atoms. What are those things that circle around atoms? Electrons. So as electrons are circling around atom, they're moving chaotically. So they don't go like, you know, the picture where it's like, right, the little nuclear sign. They move chaotically, but they do move in a direction. And using magnetic waves, you can, in most cases, reverse that direction. That means every atom of every molecule and every electron that's on there, you can change the direction of. That's a qubit register of every electron in every atom in the table. how much data could I store in the table? A lot. More than anything we could conceive of today, just in that table. Here's the thing. The universe isn't physics. It's not math. It's information. It's a giant construct of information, all intertangled. So one of the questions about, how many people have heard of quantum teleportation? This is a real thing. I'm not making it up, so there's proof. See, people have heard of it. So here's the weirdest thing, because again, we're just starting to get this. And it all comes down to time. I'm going to keep repeating this word to you until you get it. This is the problem, because you're measuring things. So if I take the information about a photon or an atom or anything in the universe, and I take the information and I move it over here, the thing winks out of existence here and winks into existence here. Because I changed the location of its description. I changed its information construct. But I didn't change the universe. The universe just, because it's all one, it didn't move, right? See, you're using time. You're thinking about time, like how did it move from, that's not a measurement of distance. Distance is a measurement of what? Time. How long did it take me to get there? How far is it? Everything we think about is time-based and wrong. So it just goes away and it just reappears over here because that's where it's supposed to be now. And that works across any distance. Now we're working as humans to move that distance along. The Chinese just did a quantum network. Now, so one of the problems with intertanglement, we can only make quantum computers that can do intertanglement between two qubits, that has to be very small, nanometers apart. They have to be very close. The reason is you move them apart, there's too much other interference from the universe that starts messing with the qubit registers, and we can't move information from this one to that one, and we can't do calculations because the intertanglement breaks as we move them apart. But we're now realizing that it's the way we're building them. So there's an article, which I'll give you guys a link to, that shows we'll never be able to transmit information across the universe because the qubits have to be very close together on a nanometer scale. But then someone figured out this thing called flip-flop qubits, which work differently, and suddenly the nanometer thing was like 10 times longer. Last month, the Chinese transmitted a quantum signal using quantum encryption from the surface of the Earth to a satellite and back to the Earth. Soon we'll be able to transmit quantum information across the universe, using the universe as a computer, because the universe is information-based. But our math that we use today is time-based. The way you think about things is time-based. It's very confusing, I get it. One of the best analogies I've heard is, take a book, big book. If you read the book all the way through, it's a linear story, right? What if you take the pages of the book and throw them all in the middle of the room? Each page is a story. It's a moment. Because that's more like how the universe works. Because of our position in the universe, we link all the pages together and give ourselves the illusion of time. But that is not how the universe works. And quantum computing takes advantage of that. That's the part that makes it difficult to understand, is you're trying to measure it using time. How fast does it do this? That's not a measurement of fast. That's a measurement of time. How many simultaneous calculations can it do? That's a measurement of time. How much distance can I get between qubits before they begin to have interference from the universe and the data becomes unusable? That's a measurement of time, not distance. I feel I've lost some of you, but some of you are trying to get it. I get it. It's hard. It's hard. Okay, so now it's your guys' chance to ask questions and totally throw it at me, because this is the best I can do. It's hard. I told you quantum computing is hard. It's weird. It gets weirder. The interference pattern is the weirdest thing I've ever seen. I've seen it done where they shoot one photon through at a time. There's no way they can interfere. And it draws the same bloody pattern. Can you hand her the mic?
All right, so give us an example of where quantum
No, no. So the biggest use of it potentially, so it's not in public domain yet. It's only in laboratories. So right now, quantum computers exist at IBM and at Intel and at Microsoft and at Google in their labs. I don't know of a quantum computer that's out in the public realm. There's many at different universities being developed. There's lots of work being done, but there's none that's publicly available. IBM announced yesterday they believe they will have a publicly available, so one of the things, let me rephrase, let me come back. So there's a measurement that everyone looks for is when will quantum computers equal current computers? Because right now they don't. Because we can only build so many qubits and we have to keep them close together, and we're still learning how to wield this technology, right? So the question is, when will it surpass a current computer? IBM says this year. That blew everyone away when they announced that in January, which it's what, January 15th or something like that now? 10th? 9th? 9th. Thank you. It's the problem with time. So that they announced early in January. They're already coming back and saying, not only do they believe that, they believe in just a few years, they will have quantum computers that you'll be able to buy that will exceed all computers made. We're at the precipice of a giant explosion in computing power because we're eliminating this from the computational argument.
All right, how big is that computer going to be?
Well, today they have to be super cold, right? So today they're giant because they have to have all types of cooling, and 420 degrees below zero was a number I heard about one of them, in order to maintain that qubit nanometer connection and eliminate interference. As we learn new techniques, right, like the flip-flop one that just came out, we'll learn techniques that can reduce interference from the universe and make those more stable. And that will make them better. One of the things that you're also thinking of is you're thinking in the past. There it is again. You're thinking about a computer that goes under your desk. Anybody want one of those anymore? Yeah. No, you want to... Right, but your cell phone doesn't do it in the future. It doesn't do it now. 90% of what's running on that cell phone is running where? In the cloud. So think of it more that way. Unlimited computing power tied to your phone, running in giant protected server rooms. That's the future of computing in general, but certainly of quantum computing. Because these things are delicate, right? If you shake them or bump them, they won't work. Because they're wielding such small things simultaneously. But that's also because it's the same thing. Go back to the beginning of computer science, right? Go back to the very beginning. The first chips we ever made were terrible, flawed things. These first quantum computers are going to be terrible, flawed things, but it's what they will become, right? It's as we learn this technology and all the stuff you're baffled by, like people were baffled in the 1960s, right? When we started talking about how computers work, people were like, I don't get it, right? This is the same thing. It's new. This whole concept, everything I've told you, the base technology, the base physics is new to most people. You got to get over that because that's the future. That's where we're going. Make sense? Can you pass him the mic?
Can I ask a question?
Sure, of course. Yeah, please.
Digits, yeah.
Or dollars. Dollars would be better than digits.
I wondered if the mechanism of trying to find prime numbers would be an example of proving to the public how vastly impressive the quantum computing might be.
Absolutely. And go ahead and hand that down. The first things we're doing is we're building custom-built quantum computers to do a specific task. Because here's the other problem. All the decades we've spent writing software are now useless, right? All of our software works like this, in linear time, not like this. We don't even have the concept of superposition and entanglement in operating systems. We have to start over from scratch. So today, the ones that are being built in the labs are to do a specific thing, like calculate a floating point integer, or look at disease, or very small, achievable, mostly mathematical problems that our traditional computers just aren't good at. Now, doesn't that sound weird? Our traditional computers aren't good at math. Sure they are. They're way better than we are, right? They were miraculous devices. I use the word were because their time is over. This is the new thing. This is what's going to come next. Go ahead, please.
Yeah, that goes to my next question is, as an entrepreneur, how can I get time on a quantum computer and figure out what to do with it?
Well, interestingly, both Google and IBM are working very hard to, here, start a new session, to produce cloud-based quantum computers that people can access for that exact reason. Because it's good press for them, right? They want to be able to say, first, we have the first quantum computer in the cloud that you can rent by the hour, or we'll just give it to you for free, right? Google has an AI right now that they'll give away for free that you can go ahead and start building your own artificial intelligence type programs. They want all of the manufacturers of this, all the research places, everyone that's spending just scads of money on this, right? Whoever gets here first wins. This is starting over. We just started over. Completely from scratch, computing. Because we have to get rid of the time problem. We have to stop doing it the way we've been doing it. And we have to start over with a completely new concept.
But isn't that like kind of the way we think? Like, if we're going to solve a problem, we kind of address it in a logical, linear fashion in order to break it down in small pieces.
No. We don't work that way at all. We use probabilities. Right? We use superposition. We're thinking many things simultaneously and we're calculating things and we're weighing the odds, right? And then we choose a choice, like the cat reveals itself and we go, right or wrong. We work more fuzzy. We're more like a quantum computer because that's how the universe works. And again, I want to stress this. Our math today, like our computer science today, like our computer software technology today, is all built on this concept of sequential time. And it's fundamentally not how the universe works. It's an important concept you have to keep coming back to so you understand when you see things. Can you pass that mic over that way? When you see things that have been such staples of our lives for thousands of years are suddenly gone because they really are no longer relevant, like clocks.
So for some of us growing up, we grew up without computers. For our kids, our grandkids, it's second nature. They grew up with computers.
And they're different. The way they think about it is different, yeah.
So our kids, our grandkids, from here on out, when will that happen? Where they're growing up with quantum?
Well, there's a problem with that. It's the whole kids and grandkids thing. So, I'm trying to make this work. I'm going to give up on that because it's technology and it's defeating me, as it always does. Don't laugh, Hans. So, here's the problem. One of the things that this will enable is us to fundamentally understand the universe, which we don't. So, one of the things that is part of AEON3, that those of you who have been here for a while have heard me talk about this, we're trapped on the surface of this planet as organic human beings. We might make it to Mars. We'll probably kill a lot of people doing that. We're never going to make it to Saturn as organic humans. You can't leave the surface of this rock in this machine, right? You can't. You just can't. The concept of building a lifeboat, a ragtag fleet of ships sailing across the universe in Battlestar Galactica is never going to happen. Organic humans cannot live off of the Earth for many reasons, not just cosmic radiation and gamma bursts and all the things you think about. We just can't do it. Our concepts of time and the way we live and the way we think of ourselves and how we raise our children is built on this linear, fake time structure. As soon as you move outside the little shield of this beautiful little thing we live on, all that's gone. And you mentally can't do it. There's so many things about it that are negative, you just can't do it. Did you have a statement or a question? I see it in your face.
I'm not sure it's a question, it's more of an observation, based on the things we've talked about all this time. But if we can master these, make these quantum computers, if we can master the information available in the universe, we may not have to go there to see it.
Sure. Well, here's the thing.
We have access to the information directly.
Right, connect to it directly. So here's one of the things. A lot of people don't understand why we're not hearing things from SETI, right? The search for extraterrestrial intelligence. When we look, what are we looking for? Radio waves. No advanced species would use radio waves. They would use quantum entanglement, right? And superposition. across the universe, 0 weight state. If you send a radio wave out into space, how long does it take to get to Mars? Anyone know? 8 minutes. That's 6 minutes, but still, it's a really long time. And I may be wrong on the 6. Somebody should look it up. But it takes minutes. That's why the Mars rover crashed into a rock. Because by the time we realized it was headed towards a rock and then tried to turn it, so much time had gone by that the bloody thing crashed and got stuck. Now it's sitting there. For all this time, we have this one picture. This is great. We spent all that money, right? If you had a way to use quantum intertanglement across quantum distances, that information would be there actually before you thought of sending it, because it's already there. Because everything in the universe is happening at the same time. There is no such thing as time. So your ability to explore the universe would become possible. Get it? It's a totally different concept than everything that we live on today, because everything up to this point for human beings has been about where we live on the surface of the planet. Hi. So that makes it very difficult for us to grasp what does it mean to move to a different position, right? So if I was here and I am on Earth and I'm in some type of organic body that I've constructed, but my mind is being housed in a quantum computer, right? Now, I take that information about my mind and I somehow, this is the tricky part that we don't know how to do yet, move that information to another point in space-time, anywhere in the universe. My mind would wink into existence there. Get it? You can be stored in the fabric of the universe, in the table like I was talking about. The universe is structured on information. And that's why you don't get quantum computing, because it's connected. It's all part of this. We're just figuring out for the first time ever how to build a qubit and how to intertangle it with the qubit next to it and how to get it to exchange information. And from that, we're getting all kinds of inordinate growth in computing power, but we're also getting things like quantum teleportation and intertanglement and all kinds of things we didn't expect, because we knew this from physics. Physicists have been telling us for years, this is the way it works. They've been trying to explain it. Schrodinger is long ago dead. The cat apparently lives on, right? But they've known this forever. This is the first true practical application that's going to affect every one of you, right? The first time it's going to smack you in the face is quantum computing. Somebody pass him a mic. Oh, he's already got this. That was weird. That was like there was no time. It was just there.
If I remember correctly, and please reiterate me if I'm wrong, you said that everything we know right now of life and everything we know for math and everything is wrong, because quantum computing, it has like its own way of doing everything. Does that mean that we would have to relearn everything we know as of right now, completely we have to relearn everything about life as we know right now?
Sort of. So yes and no. So our physics are right? Our physicists have figured this out long ago. They just can't explain it to the rest of us. But when you do it, if you're a mathematician and you do this, you get it right away, right? It's obvious that this is the truth of the universe. This is how the universe works. The first practical application, I think, is quantum computing. It's the first time it's come from research, from physics, from theoretical physics, right? Sorry, to research, to building something that actually does something. And that's brilliant. So the math that's built on is good. To go to the next step, though, the real thing we'll have to rework is software. Software is really off in the wrong direction. Yeah. From scratch. Yeah. Yeah, most computer science, and if you think about how chips are built, how everything is built on a mechanical logic gate, right? So it's all positions and on off, and it's all built on assembly language and then layers of abstraction from that, right? All that's got to go. We need a new basic concept of software, and I'll tell you, that's what's going to hold back quantum computing, not the linking of the intertanglement between qubits of 40 nanometers to 80 nanometers to the entire scope of the universe. That's not the problem. Humans are real wily, right? Once they're onto a problem, they'll figure it out. And already the explosion in separating the qubits and keeping them stable and getting that information to transfer is exploding. That's not the problem. The problem is, think how long it took us to write all the software that we have now. Early computing was slow, right? Because we were writing in assembly language. It was terrible. And then we started to get more modern languages that built more abstraction and made it so more common folks like myself could actually write software code, right? Now we have it where you can actually just go onto some cloud and link different blocks together and build a program, boom, and then it runs on your iPhone. It's amazing, right? That would have taken years in years past. That's what we have to start over from scratch doing. And it's, yeah, please.
One more question. So since you said earlier that you can kind of transfer your mind to a different place or whatever like that. With your knowledge and your experience, do you believe that in the future this is our way for evolutionizing our species, like that's who we are, like just be able to take that new step, I guess, for our species?
Sure. So yeah, so that's like I said, it is the cornerstone. It's the fundamental building block of the third eon of mankind. The way that we can build the things we envision, right? If you want to take yourself and put yourself in a computer, you don't want to do it in a linear operating, binary, fallible computer. That would not, I vote no, right? How many times blue screens to death, right? Let's have a new software package on a new computing platform that I'm living on. That's a really bad idea. But if it's something that's connected to the fabric of the universe and is indestructible, unbreakable by humans, right? Think about this. It's in the fabric. It's in the structure of the table. It's so much simpler. We just haven't been wielding this tool yet. We're just starting now. But when you get 50, 100 years out from now, which is where most folks, myself included, calculate when the third eon will happen somewhere around 2100, that is when this payoff comes. Because now I could take and calculate every position of every molecule in your body, right? Not just your synaptic gaps, the things that Kurzweil's been talking about for 30 years. No, that's too small. I could calculate everything and move that to a different substrate. And at the same time we do that, this will enable an explosion of the understanding of biology, right? Because our medical science will rocket forward as we can simulate biological structures in ways we just can't do with traditional computers. That's going to be in 20 years. The end of disease, you guys have heard this from me before, from AEON3 people. The end of disease, the end of aging, the end of anything negative about being human, which will result in other problems, overpopulation, stagnation, we'll get bored, right? We won't become innovative. Everyone looks 23, how fun is that? Sounds cool, but it's kind of weird, right? So how do we get past that to something bigger? Turns out we're living in this amazing universe that's filled with things for us to go do. We cannot do it without this thing. This thing is the thing that makes all other things possible. No, it's just working the fabric of the universe, right? Just like we work metal today, or we work computer science, or we work math. We do the same things today with different materials. This is using the materials of the universe in order to do calculations. Nothing more. What we do with that is all us, right? You could use this to simulate all kinds of things, right? To know how things work. The big question is, what things do you want to simulate? Which is that list I put up earlier. Those are the things we already know. Can you pass the mic back there? Okay. What time is it getting to be? Anybody time? Oh, wow, that went fast. Please.
So you seem pretty certain that it's just a matter of certain amount of time before we get to that place where that reality, quantum reality is in computers and et cetera. So how are you and how are others who are in this field so certain that they're not going to hit a stumbling block that would prevent, like there's just something that they can't penetrate?
Sure. Great question.
Like say, string theory really hasn't, gotten anywhere.
Right.
How's this going to get somewhere?
Yep, great question. So the answer to that lies in, look at what we did with traditional computing, right? We ran into a constant string of impassable roadblocks, one of which we're still living with, hard drives. Why do we have memory chips in computers? Because hard drives suck. Hard drives are terrible. They're so slow and so breakable and so bad that when we turn on the computer, we take the information off the hard drive and load it into memory so that it can be moved in and out of the processor faster, because hard drives suck. We've been trying, since we invented a processor, to feed information in and out of the processor like RAM in something that isn't volatile, that doesn't go away when you turn the power off. We've tried a million different things, right? Everyone remember chemical computing? We tried everything. None of it worked. We still have hard drives because we never solved that problem. What did we do? We created memory chips to work around it. That's what humans do. That's my answer to you. Once humans are onto a thing and they get it, you're not going to stop them, right? They're going to find a way to wield this power, to solve these problems. That's what we're best at. And if we had a partner that could handle the big logic, the big simulations, where we could come up with the ideas and it could help us through an artificial intelligence running on a quantum engine, right? Doing parallel processing to massive scale with giant amounts of data, human creativity could truly be unleashed. So I think the problems we're going to run into, which is already happening, we're going to solve more quickly because we literally have a better tool to help us solve those problems than we did with traditional binary silicon-based transistor-based computers. You got to use mic. Other people are like, what? Oh, Raj, yes, sorry. He was first. Sorry, I apologize.
I just want to bring things back to the mandate of what AEON3 is about.
Yeah.
You talked about, or you alluded to the fabric of the universe as one. Everything is interconnected. That's why we have this non-time. So what you're essentially saying is science is now only just catching up to what spirituality has always known, that there is a cosmic mind that we're tapping into. That is actually this matrix, if you want.
In many ways, I agree with that. Yeah, I think a lot of scientists are coming around to that basic concept. I've seen the bearing of the hatchet between science and religion, which was clearly an issue a while ago, and isn't so much of an issue anymore, as the two are coming together in, I think, a kind of unique way. Science wants things that are provable and repeatable, right? And this is provable and repeatable. We know this is how it works. The fact that it coincides with a lot of traditional religious thinking, I don't think is lost on a lot of scientists. It just, to them, I think it happened that way, but to me personally, I think it does. I think it's exactly that. I think we're seeking the same thing. I look at traditional mysticism or religion sometimes as a way to get around doing the work, because you can observe stuff and you know it's true. Right? If I observe this interference pattern and I did the one photon at a time, I know it's true, but I don't know why or how it works. Science isn't concerned. Science and religion are seeking the same truth. One is just interested in the truth, the other one's interested in how it works. Make sense? So I do think it's inevitable that they were going to come back around together. And this is it. This is the beginning of the third eon. We go just this much farther down this path and we're rocketing forward. You're going to see everything that has been talked about for the last 20, 30 years just burst onto the scene. Do you have a question?
Does that mean like the way data traditionally moves, like through Ethernet cable or on a satellite, is going to change as well?
Sure. So the Chinese quantum network. So one of the things about quantum networks, because the particles are entangled, it's zero weight state. Okay, so when you use a network today, when you plug into the wall, right, old school, there was 10 megabit? I think I got it, 10 megabit, and then went to 100 megabit. Now we're at 1,000 megabit. And then we're going to go to 10,000, I think. And when you look at Wi-Fi repeaters, they're, this, right? All zero, instantaneous.
So that reminds me of like Ender's Game and like Ensemble. That
Mm-hmm.
used to communicate with spaceships or something like
Absolutely.
that. Or like Snow Crash, where you plug into virtual reality and you can see anything in maybe a different world or something.
Yep. Exactly true. So one of the things that is a super good use of quantum computing is telepresence. I want to project my moment somewhere else in space-time. So Joyce asked the question in the last open mic night about time, which I tried to explain it, and I don't know how good I did, but I'm going to try it again. The universe is a ball of time where everything has already happened, is happening at the same time. Everything, it's one. That's how it works. When you observe a moment in space-time, you're opening the door and looking at the cat. And so you see the cat. If you could use quantum teleportation and quantum mechanics, it is theoretically conceivable that you could open a window and look at any point in time, anywhere in the universe. When you look out at the stars, you know you're looking millions or billions of years into that star's past. You guys know that, right? Because it took the light so long to get here, so you're seeing it in the past. And if you went towards it at light speed, it would just be frozen in time until you got there, and then you'd be there today, which was the moment you left. Physics is hard, sorry guys. That was what consumed Einstein, was light. He was focused on light. And again, at the end of his career, he realized he should have been focused on time. Time was the thing that we all think is real that isn't. And it has no place in quantum computing. That's why I'm dwelling on it so much. When you run a quantum network, theoretically the answer is there before you ask the question, before you transmitted it. Because it's not concerned, it's you organizing the way to ask the question that then produces the answer. Software is going to be our problem here, big time, because our software doesn't work like that today. We don't even think like that today. No one in computer science writes software like that today that I know of, other than a few IBM lab researchers and a few other guys. Sir, can you pass the mic around? Hopefully you guys are like looking stuff up on your phone so you know I'm not crazy, right? Because this does sound a little crazy.
So in embracing this, as we get quantum computing and start to delve into it, we might get help from other intelligence within the universe that will point us in that right way.
God, I hope so. So here's an interesting thing. Why hasn't SETI or other search organizations switched to looking for quantum changes in quantum fluctuations and entanglements? Because we don't have a way to yet. We're so new at this, there is no machine to look for this yet. I do believe that once we start looking for this, we'll probably find something out there, but not radio waves. How long ago did humans create radio waves on any scale that we were broadcasting them into space? 1930s, World War II, really. The first time we built transmitters that could broadcast a radio wave to space. When are they going to go away? So 1930s to 2100, maybe sometime before 2100. That's a very short amount of time when you're talking about the universe. You could look for radio waves till you turn blue, you're never going to find one. Because no advanced species would propagate a radio wave through space-time. It indicates that you as a species do not understand that there is no time. It's a time-based broadcast transmission. Get it? It's old school. You guys are doing good. I feel like you're catching up now. I feel like you're on it. You're kind of like nodding, going, I kind of get it. I still don't, but I think I do. Anybody else? Can you pass the mic back? Then we got to wrap it up on here, but we'll keep going here if you guys want. But we'll take the mics off and stuff and say goodbye to the people on Facebook who have been very patient.
So kind of get into this like paradoxical sort of situation where, I mean, what you just told, what you just said, to me strikes as kind of a paradox, where if time's not real, yet so then what the heck are we doing? Like, if we can know any point in the future, any point in the past, and like the mystery's kind of gone. I mean, so.
I didn't tell you the other half of the story. So that is the ball, and it's everything at once, right? Everything in the ball is being chaotic. Everybody's doing their own thing. Because again, when you're measuring the future and the past, what are you doing? You're measuring time. If the universe is truly timeless, all things are happening simultaneously, there is no time. But it still allows for chaos. So as we're going through our lives, we're contributing to the chaotic fabric of the universe. One of the things Raj will tell you, one of my favorite sayings about human beings and about creatures in general. Everything that ever is, ever was, and ever will be is absolutely perfect because it's contributing to the growth of the universe, of the information in the universe. We're all making the universe better because we're being chaotic, but there's no time. It's all happening at the same time. So if you were to observe a point in time and then stop observing it, put the cat back and close the box, is the cat dead or alive? Come back and observe it again. It might be different at that moment in time. It's also chaotic. When people talk about time and going back in time, you're starting from the basic question is wrong. There's no going back in time because you're measuring time again. Start playing this game with yourself when you start thinking about these things over the next few days. Start thinking about how many times you're counting time or distance, which is time, right? It's bizarre. It's how we are programmed and wired to think because it's what we observe. It does not mean it's true. It just is what we do. So I'm just going to take 1 second and we'll come back to more questions. So thanks very much, everyone on Facebook. Please go ahead and post your questions and any comments you have. I really appreciate you guys hanging out. And we're going to say goodbye to everybody on Facebook. Everybody say goodbye. Bye. Thanks, you guys.